Here's an optimization problem. I can tell it's an optimization problem because I have the magic word right here, maximum. I want to find the maximum area that 1,500 feet of fence can enclose. So, draw a picture and assign variables. This very definitely is going to be helped by drawing a picture. A farmer wants to put a fence around a rectangular field. Okay, I know what a rectangle is. There's a rectangle. I'm going to name some variables. I'm looking for area ultimately. So length and width seem to lend themselves. It doesn't matter. You can call them X and Y if you want. What else? Rectangular field. I'm going to subdivide the area into 3 smaller plots by putting lengths of fence parallel to one side. So I want 3 little rectangles like that. So I have, I don't know, I'm going to put the cows in one and the pigs in another one and the chickens in the third one or something. Let's see, maximize area. So my goal is maximizing the area. The area of a rectangle is length times width, and there's my function that I want to maximize. But there's a problem with that, and that is it has 2 variables in it, and I'm only allowed 1. So we'll look for a constraint here. The constraint is just an additional piece of information, and that is we have 1,500 feet of fence available. So 1,500 feet of fence must be, I'm going to have to go all the way around the outside, so that's 2 lengths and 2 widths plus these 2 extra in the middle of the rectangle there that are the length, that have a length of W. So that's total of 2L, the way I have it labeled, and 4W. I can now solve this for, it doesn't really make a difference for this particular problem. If there's one variable that's a lot easier to solve for than the other one, pick the easy one. But this one, it doesn't really matter. So I'm going to solve for L in terms of W. And if I do that, I have 750 minus 2W. So I'm going to subtract 4W and divide everything by 2. There it is. Now I'm going to take that and substitute it into my area equation up here. L is 750 minus 2W. So there's L times W. The area of the rectangle is length times width. And now I have everything in terms of one variable, W. So here's my function that I want to maximize. I'm going to go ahead and distribute for ease of taking derivatives, which is going to be our next thing in a minute. There's the function. I want to maximize the area. Now we're ready. Let's take a derivative. There it is. I'm going to set that equal to 0 and solve to find critical numbers. If I add 4W on both sides and divide by 4, I get 187.5 feet. So length of W is 187.5, which means the length is 750 minus 2 times that. Which is 375. Have we answered the question yet? No, we have not. The question was, what's the maximum area? So it's nice that the length is 375. Well, we can use that, I guess. So the area, length times width. And we get Breaking out the calculator for this. Sometimes I can multiply, not numbers that look like this. So if you can do that, yay. 70,312 and a half. That's area, so we're going to be in square feet. And we have answered the question. Just to make sure that we've found a maximum and not accidentally found a minimum, I'm going to go ahead and take another derivative. Which is -4, looks like, the derivative of the first derivative, which is less than 0 no matter what. Second derivative test says if the second derivative is negative, then I've found a maximum, which is what I wanted, and there we go.